Hello, friendly people. This is Dr. Benton, and this is our lecture on global winds. This is our first part on global winds. We're talking about the Coriolis effect here. So first, a warm-up question. What causes global winds? And there's the meme of the day on the side. So we talked about wind before the break. We said that wind is the movement of air. Air moves from high density to low density places, from high pressure to low pressure. The density, that pressure, changes because the temperature changes. When it gets cold, the density increases, so cold air has high pressure, it sinks, and the wind moves away from the high pressure. Heat, on the other hand, creates low density, low pressure areas. The hot air rises and it sucks air in. So it's the temperature differences that create the pressure differences that cause wind. That's true for local winds, and that's true for global winds. And here you see that the H that stands for high pressure is blue because cold causes high pressure. Here you can see the L that stands for low pressure is red because heat causes low pressure. So cold and high, warm and low. Local wind systems happen in a local region, over a couple of miles. And so these are places like the coast, because land and water heat up at different rates. The land, we said, has a lower heat capacity, so it gets hotter faster. During the day, it gets hotter than the water. That means that the pressure over land is lower than the water. Well, air from the water that's higher pressure moves into that low pressure area. We call that a sea breeze because it comes from the sea. And this is the local wind system. It's going from the higher pressure to the lower pressure, from the colder temperature to the warmer temperature. Land breezes, the other local wind system we learned about, the exact same process, opposite direction. At night, they're both cooling down. The ocean cools down, the land cools down, but the land gets colder than the water. So the air here is higher pressure than the water. Air blows from the higher pressure to the lower pressure. So again, this is an example of circulation, convection current, I should say. These convection currents are caused by temperature differences, and we learned that convection is a method of heat transfer. It's all about temperature. Well, global winds on a global scale are caused by global temperature differences. Specifically, the biggest global temperature difference you can get is the difference between the poles and the equator. We learned back when we talked about seasons that the most direct sunlight lands on the equator. The least direct sunlight lands near the poles because these are at the greatest angle. So this indirect sunlight doesn't add much warmth, it leaves it cold. This direct sunlight makes the equator very warm. That warm air at the equator has a very low pressure. The cold air at the poles has a high pressure. And so the wind moves from high to low pressure, from high to low pressure. Each pole moves towards the equator. And of course, we're looking at the arrows on the bottom against the surface of the Earth. One, because that's where we live, on the surface of the Earth. That's what we care about. But two, it's the land that's giving the air its temperature. When that air is over cold land, it becomes cold. When that air is over warm land, it becomes warm. If it's over wet land, then it becomes wet. The air takes the properties around it. So this is cold air moving from where it's more dense to where it's less dense. And again, convection currents. So this is the simplest possible model to explain that convection. Again, we have the blue H because cold makes high pressure, and it flows towards the red L because red is low pressure. It's going from this pole towards the equator, and it's also going from this pole towards the equator. We can see that at the equator, the air actually rises because hot air rises, and then it cools down and it moves back towards the poles to complete the circulation. That actually creates what's called a circulation cell. And so in this very simple model, there's only one circulation cell. The air moves from the cold to the warm, then it rises and moves back. And it creates a continuous cycle, just like those convection currents in the mantle we learned about. It's a cycle. And here we see another diagram showing the exact same thing, that single cell circulation. The cold, high-pressure air sinks and moves downwards, sinks towards the surface and moves towards the equator. At the equator, it heats up, it rises, and it spreads back out. Now, there's three major differences between global wind systems and local wind systems. The first one, as you can imagine, is the size. Global winds are global. We're talking about thousands of miles. Local winds happen across a few miles. It's not very much. It's not very far. They work on small temperature changes. Here, we're talking about huge temperature changes across the surface of the Earth, thousands of miles, global scale. Number two, though, is the circulation pattern. Because local winds change directions twice a day. When the land gets hotter, it blows towards the land, and when the land gets colder, it blows away from the land. The wind changes directions twice a day because the temperature changes twice a day. But here, there's no real change in temperature. The equator is always going to be hotter. The poles are always going to be colder. So all day, every day, we have high pressure at the North Pole because it's cold at the North Pole. We always have low pressure at the equator because it's always cold at the equator. The third big difference, and this is probably the most confusing part of the unit, is the Coriolis effect. The Coriolis effect, as we hopefully learn from our definition on the slides, has to do with the way the air curves as it's moving from the poles to the equator. The air actually appears to bend. The air doesn't actually bend. It's actually the Earth that's moving. But since we're on the Earth, we don't see the Earth moving with us. These are some videos that explain it. I'm going to post these in a second ed puzzle in a moment. So watch these links next. They're all going to be in the same ed puzzle. But what I'm talking about here is frame of reference. If I'm standing on the ground next to a tree, I can tell that the tree is standing still. And if I'm looking at a car or a train, I can tell that that's moving, right? The car is moving, the train is moving. But what if I'm in that car? If I'm in that car, I'm not moving, I'm sitting still. The dashboard is staying at the same position in front of me. The car door is still right beside me. I'm not really moving inside that car, right? But if I look out the window, I see the tree moving backwards. The tree's in front of me, then it's beside me, then it's behind me. So it looks like the tree is moving. It all depends on your perspective. This is also showing that. A person is standing still inside a moving boxcar. They know they're standing still. They're not moving. But this other person on the ground says, no, you're definitely moving. You're running away from me. So what is it? Is she moving? Is she staying still? The answer is both. It depends on your frame of reference. It depends on where you're looking from. If we were looking from the wind's direction, we would see that the Earth is spinning. But we're stuck on the Earth. We're spinning with the Earth. So what we actually see is that the air appears to move. The air bends in a curve. And this is what the Coriolis effect is. The wind wants to blow straight from the pole towards the equator, but the Earth is a moving target. By the time it reaches this point, 0, the Earth has already moved. We're now at negative 15 degrees. The Earth rotates by about 15 degrees per hour. So we're stuck to the ground. We don't see the Earth move, we see the wind move. In reality, what's happening is the Earth is literally moving out of the path of the wind. But since we're fixed in our location on Earth, and since every map shows a fixed position of the Earth, the global winds are what we see as being curved. It's the curving of these global winds. So let's take another look at this. If I'm standing on top of the North Pole, looking down at the Earth, looking down at the axis, the Earth is spinning in this direction, to the east. The Earth is spinning from the North Pole counterclockwise. Well, what that means is that everything else that I see spinning spins counterclockwise in the northern hemisphere. The reason being is that objects keep getting deflected to the right in the northern hemisphere. I put two big arrows here because these are two major concepts. Objects always move to the right, always deflect to the right because of the Coriolis effect in the northern hemisphere. South Pole's opposite, though. If I was standing at the South Pole, looking up at the Earth, looking up at the axis, I would actually see the Earth spinning clockwise from my direction. Still moving to the east, but in this case clockwise because I'm upside down. Well, in the southern hemisphere, that's exactly what happens. We see hurricanes, tropical cyclones, spinning in an opposite direction. So hurricanes, tropical storms, they spin in different directions on different sides of the equator because that's the direction we're seeing the Earth's rotation from. And we're going to learn about hurricanes in about 2 standards from now, so we're going to come back to this for sure. But the Coriolis effect is huge when it comes to global winds. Fun fact about the Coriolis effect: at our latitude, a sniper bullet drifts 2.8 inches to the right for every 1,000 yards it's traveled. Sniper rifles nowadays can travel like 3,500 yards. So you imagine, I mean, that's enough to miss a person. Snipers have to be trained enough to account for that in their calculations. So it's amazing that you can see the difference. Now, it's more than just the fact that the Earth is rotating, it's because the Earth is also a sphere. The Earth is fattest at the equator. The Earth is furthest from the axis at the equator. It pretty much touches the axis at the North and South Pole, right? So near the poles, it's actually spinning slower, about 0, as opposed to the equator, which is moving at about 1,000 miles per hour. 1,600 kilometers per hour is about 1,000 miles per hour. And we can see that that speed decreases the closer we get to the center of the axis. And that's the way tangential velocity works in a circle. Notice that these are all moving kind of at the same pace, but the red one is moving very slow. That green one is moving very fast. The green one has to move faster to keep up with the rotation. And so the further out we go, the closer to the equator we get, the faster the Earth is spinning. And you might have also noticed this on carousels, like the merry-go-rounds at an amusement park. You've got 3 rows of horses. The one on the inside is the baby horses. They move slower. The ones on the outside are the bigger horses that move faster, right? Because the further outside you are, the faster you're going to go. So when I put this together, I have the equator spinning faster and the poles spinning slower. What that means is that if I'm traveling towards the equator, the Earth moves to the east before I get there. So if I'm heading down, I bend to the right. You're left, but look at stage right. Here, though, I'm moving in the opposite direction. The Earth is actually slowing down as I go north. So I appear to be moving faster. Again, bending to the right. I always bend to the right in the northern hemisphere. I bend to the right, I bend to the right, I bend to the right, I bend to the right. No matter what direction I'm going, I bend to the right. And in the South Pole, it's the opposite. I bend to the left, I bend to the left, I bend to the left, I bend to the left. And that's because of the Coriolis effect. The air is always going to bend to the right as it moves in the northern hemisphere. The air is always going to bend to the left in the southern hemisphere. And again, these are caused by differences in temperature between the equator and the poles. We would expect it to go straight from that high pressure to low pressure, but that's not what we see because it gets curved. Now, the kicker here is that it actually curves so much that it can go perfectly horizontal. Instead of going vertical, it goes horizontal at the equator. But that happens a third of the way down. It only makes it a third of the way before it starts to turn around and spin the other direction. Well, then we have air here. It's still wanting to move through the equator, but it only makes it a third of the way before it turns around. Here we have air. It makes it a third of the way before turning around. So what that means is that we don't just have the one circulation cell like we've been talking about. We actually have 3 different circulation cells between the pole and the equator. 1, 2, 3 in the southern hemisphere, 1, 2, 3 in the northern hemisphere. And in each one, you can see the direction of the wind bend to the right, to the right, to the left, to the left. Tomorrow, we're going to learn more about these circulation cells. It should be a little simpler, but notice there's a lot of labels. And if we were in class, I'd actually make you draw a diagram like this. So, ticket out the door. Final question. What causes global winds? And this is a quote from Colin Powell. He's a 4-star general. I think he was the Secretary of State during the Bush administration. Very famous guy. There are no secrets to success. It's the result of preparation, hard work, and learning from failure. You have to work hard if you want good things.